but it never really goes to 0. Is a linear fit good for this? Clearly not. Right? We know enough to know say that linear fit doesn't work here. So what would be a good fit? Let's look at the Tukey's transformation. Jeez, I should have removed this first of it. So this is the pattern of the curve, right? So we need to try in this thing down ladder transformations in X or down ladder transformations in Y. That's what we need to check. So log was one of the things that was there. When you try log of time, what you see is almost a perfect straight line. Essentially, log is the right thing to do this if you think about it. What does log do? It larger and larger numbers, the rate of growth of large numbers is much smaller for R. So what happens is, as the proportion of time increases not linearly, but as a factor, your memory is also being lost as a factor. That's what is happening here. Okay. So this is the way you use that nonlinear transformation to do it. Still, we are doing, even though it's a nonlinear data, we are using only LM to do this fit. We are doing a linear model to do it. The moment you convert, you transform the data to log, it looks linear, and we can do a linear fit easily. Okay. So let's take a break and then talk more. Let's get started. So we talked about, when a data shows certain patterns, nonlinear transformation might be appropriate for the data. Okay. Here is one more example. So if you have gone out camping or done any of these nature survival things, when I'm starting the sentence like that, it feels like I have done it, but no, I haven't done any of that. I like my soft bed and warm blanket. But when people go out in the nature for camping, one of the ways they estimate, one way you can estimate temperature is by the chirps of the cricket. Okay. So what do I mean by chirps of the cricket? This sound, right? So the frequency of this chirp, from the frequency of the chirp, you can figure out what is the temperature. Okay. And this is how the people actually use. Why might that be a reasonable thing? Crickets are cold-blooded. Okay, they are not warm-blooded. If you remember your biology, warm-blooded animals like humans have this internal temperature regulating mechanism, right? So even when you go out into cold, your body is trying to work hard and trying to maintain your body temperature at one fixed level. So there's an internal temperature regulating mechanism. Cold-blooded animals, that's the difference. There is no internal temperature regulating mechanism. So their body temperature actually drops. When body temperature drops, automatically their body metabolism also slows down. When body metabolism slows down, the frequency of the chirp also lowers. So chirp now suddenly it's not as frequent as this. It actually goes lower, right? So this sound, 1, 2, 3, 4, 5, 6, 7, 8. You count this chirp. You count how many chirps are there in a given minute. And using that, you'll be able to figure out what the temperature is. So here is a data set that shows how this was arrived at. What's plotted here is the temperature, and what's plotted on the y-axis is this chirp frequency. The frequency of the chirp is plotted along the y-axis. Not the body temperature, ambient temperature is plotted there. And you have, this is real life. Fits are never pretty. Fits are never exact. You have a fit. This is a fit, possible fit for the temperature versus chirp count. You might think that this is not a great fit. Let me try transforming the data and look how the fit is. Over here is the log of the chirp frequency versus temperature, and you have another fit. Is this better than that? Not really. If you look at the R square, the R square might be little better on this, but if the quality of the fit generally is not substantially different, always stick to the simpler model. This is a general scientific principle we use. It's called Occam's razor. If there are two models that can explain the data, the simpler model tends to be right, or simpler model is always preferred to more complex models. So stick with the simpler model if the quality of fit does not increase, does not do dramatically better. Okay, so what we have done till now is talked about transformations of data, nonlinear transformations of data. So you are doing simple fits like this, where y instead of plotting y versus x, I'm asking you to plot y squared. Sure. Yeah. So again, right, in this we haven't done the scatter plot. You do a smooth scatter plot, you try see what the scatter plot is suggesting, and then you would try to fit it. But what I'm saying is, this is an example where you should stick with the simple one, is what I'm saying. Just to be clear, right, I mean, there were some questions on this, so let me explicitly write out what we are doing. When I am saying that previously we are plotting y versus x, right? This was a data set, whatever, different y and x values were given for example, the memory data set, right? It looks like this. The way you do this nonlinear transformation fit is the following. You take, in this particular instance, we decided that log of x was the appropriate transformation. So what I do is, in Excel, you take all of these x values, take log of x values, and plot this. Compute these values. Now take these two values and try a linear fit. That's what I'm suggesting. Okay. So in the previous example, where we did distance versus speed, stopping distance versus speed, we said that the appropriate transformation was square root of distance versus speed. So what we do is, you take this distance values and take square root of it. Now do a linear fit between these two. Okay. So generally, this whole idea of transformation, nonlinear transformation, allow you to do fit between y as a function of x square, or y as a function of x cube, or log of y as a function of x. Any of these combinations you can do. Is that clear? You're just doing one transformation. However, we still cannot do y is equal to as a function of ax square plus bx cubed plus 3 plus c. This we are not able to do. All we are doing is one simple transformation, and that linear plot we can do, right? But it's not entirely true that I can't do this. I already have the mechanism to do this. How? For a general equation like this, a polynomial, for example, a polynomial equation like this, what I can do is what is actually given to me is y value and x value is what is given to me. Two columns are given to me. I can generate another column of number x1 square and call it as x2. Take all the x values, square it, and label that top column as x2. Cube it, label that column as x3. Now it looks like y, x1, x2, x3. That's multiple linear regression. So I can totally do any polynomial because I can convert a polynomial equation into a problem of multiple linear regression. So take each one and just name that, rename it. Suddenly you have a simple multiple linear regression. Is the idea clear? In fact, there is no reason why it needs to be polynomial at all. This can be y equal to beta naught plus beta 1 x1, beta 2 x1 squared plus beta 3 of log of x or hyperbolic tangent of x. It doesn't matter what function that is. I can compute that, put it in a separate column, and then I'll have a multiple linear regression. Right? So the whole linear model is pretty powerful. It does not mean that you can handle only simple straight line patterns. You are able to handle all kinds of patterns in the data. Yeah. So again, the point is this can be done even in multiple linear regression. You actually have a multiple linear regression problem where y is given, x1 is given, x2 is given, but physics tells you that the relationship between y and x1 and x2 is not linear. Let's say the physics tells you the relationship should include an interaction term, x1 times x2, a complicated interaction term like that. Even that you can handle because you can compute x1 times x2 and call that variable as x3. And again, it becomes like a simple multiple linear regression problem. So here is a problem with that kind of data. Here you have a portfolio's risk level is measured with respect to two stocks. Okay, the data set is included. It's a fake data set, so it doesn't really mean anything, but it's included if you want to play with it. So what you are seeing is that in this case, for the given data set, are the p-values, is the model significant? 0.02, right? So it's less than your 5% threshold. Model is significant. Are the individual variables significant? How bizarre is that? The model has two independent variables. It's telling you that the model is significant, right? That there is some information in that. But the p-values of either one of those coefficients are not significant, right? It could mean multiple things. In this case, what it means is that actually there is a nonlinear interaction. The moment I put a nonlinear interaction term, stock 2 times stock 3, take the product of x1 times x2 and create a new column x3 with that. Now do multiple linear regression with 3 columns together. Suddenly, I find out the significance level. The significance level of that increases. Okay. Linear regression handling complex interactions, nonlinear interactions. That's what is happening here. Yes. And that's bizarre, right? We'll clarify that in the next less than half an hour. We'll come to that. But that's the thing, right? The presence of one is going to affect the quality of fit of others. Let's think about what the each slope means, right? What the each slope means is that when you this slope means that if all the other variables are constant, if all the other variables are constant, one unit of this moving changes by y by this much. That's what it means, right? In the previous case, when I say when all variables are constant, it means when stock 3's price is fixed and stock 2's price is all that's changed, y value changes by that much. That's what it means. Now, if you look at here, it's saying when stock 3 price is kept at some number and this product is kept at some number, right? Now it's a different set of things that are being kept constant. So obviously this value is different. Yeah. Correct. I know. So this is a mathematically rigorous step making no assumptions. I'm just doing a variable definition. X1 square, from now on, I'm going to call it as X2. There is nothing that's stopping me from doing that, right? I'm just renaming the variable. But I know why you're feeling uncomfortable. It feels like I'm trying to create a new information from the existing information itself, right? I am not making any statement that this information is independent of that information. That's not what I'm saying. I am just doing a renaming transform, and now this looks like again a linear problem. Yeah. Yes. See, all I'm saying is I am doing this variable rename that I can do regardless of what the correlation numbers are. Regardless of what the variation number correlation numbers, I'm just renaming it, right? That's a mathematically well defined thing. What you are bothered by is that it feels like I'm cheating. I'm trying to create new information out of the old one. And there is a further step when we come to model building. You will see there is a way to check whether this added information actually has useful information or not. And we will come there. If I don't address it by then, just ask me that again. But there is nothing mathematically fishy about this particular operation. But I understand why you're feeling a little uncomfortable. It feels like I'm creating new information out of the old one itself. It's not really, that's not really happening here. Okay, so you can handle even nonlinear interactions with this kind of technique. Is the idea clear what I'm doing? If you accept that multiple linear regression can be done, many of these simple nonlinearities can be, you know, by hand computed, and uh, you know, you can solve it as a simple linear regression. Okay, let me just show you how this is done with an R example. Okay. Um, Sorry. So the car stop example, I'm reading the data set, speed versus stopping distance. Okay, I can uh, plot this. And the keyboard is different from mine, and I'm struggling. Car stop. So that's the speed versus uh, stopping distance example. And if I can easily plot the smooth line here. This one, right? The scatter dot smooth. That's what plots this thing. This is the one that we saw that it has a gives us a quadratic fit. Okay. So as I said, I can try and do a linear model. So LM out is linear model between stopping distance, car stop, stopping distance as a function of car stop speed. So those are the outputs for the uh, linear model. It has an intercept of minus 20 in this case. Summary of LM out gives you a R squared, adjusted R squared of about 0.87. I don't know what's happening with this projector. Adjusted R squared of 0.87. Oh, whenever I click on the R screen, the projector goes off for whatever reason. I can do a different kind of fit. I can do a squared fit instead of stopping distance versus speed. So here I'm trying to build a linear model, stopping distance as a function of speed. We talked about how the stopping distance is a function of speed, square of speed, right? So the way I build that is identity this. So now I've built a model with as a function of square of speed. Okay, I could have built another model with a function of uh, cube as well. In fact, I can build of linear plus quadratic plus log of speed. I can do all kinds of combinations with this. So here. So in this case, I'm just building square of speed, but I could have also done linear. So this has a linear term and a quadratic term. I could have put in both as well. All of them I'm handling with the linear model mechanism. Okay, because underlying what it does is it takes each one of the terms. This term it calls as x1. The next term, which is square, it's going to call as x2. X1 and x2, and it considers that as a multiple linear regression problem and solves it. So this additional term, I can add log term or exponential term or hyperbolic tangent term. It doesn't matter. It doesn't matter what type of nonlinearity I'm going to add. It will still be able to solve it using a linear in the linear framework. It does it as a multiple linear regression analysis. That's what it does. Any questions before we move on? Okay, the next topic that we are going to do is how to deal with categorical predictors. Sometimes your data set will have analog numbers. In addition, it might have a categorical predictor. Okay. For example, we talked about the value of house, right? We talked about the house, the possible predictors being um, square footage of the house, number of bathrooms and bedrooms, the overall square feet, the age of the house, all that. But in addition, one potentially useful predictor is is that a single family is an independent home or an apartment. That's a potentially useful predictor. That one is not an analog variable. That's a categorical variable. And that categorical variable is important in determining the price. This linear model, every single variable that we have given, they are all analog variables. No categorical, there was no room for categorical variables. How do you handle categorical variable is what the next section is about. Okay. So the way you handle categorical variable is in the case of the example that I gave, I talked about is either independent home or apartment, right? Those are the two categories that I gave. There could be, you can imagine a situation where your data set has multiple categories: a single family home, apartment, or maybe a houseboat. I don't know what other categories. It is possible that there are some categorical variables that have multiple categories. The method I'm suggesting applies for all of those cases. No matter how many categories are there in your categorical variables, it can handle it. The way it handles it is, if there are n different categories in a given variable, you create n minus 1 dummy variables. Okay. So, for example, if the categorical variable that is being dealt with talks about different regions of the country as north, east, and west, south, we break the so there are 4 possible categorical choices. We break that up into 3 separate categorical choices in the following way. It's broken up into 3 categories: north, west, and south. When the actual categorical value is north, is 1, when it's north, then you put north to be 1. When the actual categorical variable is east and the categories you created are north, west, and south, then all of them are remaining 0. Right? So you need only 3 categorical variables to represent 4 categories. When all of them are 0, it means the 4th category is true. Okay. So what you have done is you have converted categorical variable into n minus 1, 0 or 1 variables. Okay. Now this 0 or 1 variable can be put into a regression equation and the regression fit can be done. Yeah. Because now you change all those categorical values into some numbers. Regression can handle numbers, so it can happily do this particular trick. One categorical variable is moving into 3 dummy variables. The dummy variable can take only 0 or 1 value. The regression fit will not actually know that it can take only 0 or 1. It will think that it's some analog number and it will fit a line. But there is no situation in which it's going to be tested with any other values. It's going to be, when you're doing a test set, when a new forecast has to be done, the forecast will have only these numbers. So you can translate that number into appropriate zeros or 1 and evaluate the regression value and then give your final answer. So any categorical variable can be converted using this. Is the idea clear? Yeah. So in that case, that was a country label. The actual, we were not trying to do a regression with that label. Here, you might be trying to do regression with this categorical variable. The house price might depend on which region you're talking about. So you want to include this into the regression. If the number of categories is equal to total number of data points, then you don't have any use at all of those categories. When you have huge number of data points, the number of categories are limited, then the number of these categories could potentially affect your regression output. You include that into your regression model. Okay. Whether the customer will buy the house or not, you are making a categorical decision. Your dependent variable is categorical. We haven't talked about how to handle that. We are talking about the case where the dependent variable is analog, price of the house. And the independent variable can be categorical. That I'm telling you how to do it. When the dependent variable is categorical, how to do it is something that we'll talk in logistic regression in next class. Yeah. N-1 is a hard rule. Like finally there is one hard rule. Depends is not the answer. Yeah. No, log to base 2 of what? Right. But log of what? Number of possibilities. But what will you put in your regression equation? You can't take log of naught. Correct. So you could, good, thank you. So that's a good suggestion. However, you are now suddenly you are making one variable clearly as there is an order. One would be lower and the other one is higher. That's what you are suggesting. This is when there is no order in the variables, in the categorical variables. When there is no order and it's pure categories, you are dividing it into n-1 categories. No, yeah, exactly. But how? I'm not sure, because you are saying it can be divided into two variables, right? So let's say it will be north south and east west. Okay. So north you are going to call as 1, south you are going to call as 0. Correct? Okay. So yeah, so 0 0 0 1, and then again you need 0 0 0 1 for east and west. Um, Correct. You are giving binary code of it, so you are giving 4 codes. 4 codes you are giving totally. I am doing it with 3 codes. I am doing it as 100. I actually no. I think this is what you are saying. Effectively, is this you are thinking of it as 4 codes, and those 4 codes, one of them is not needed. One of the codes is not needed. Okay, we can talk in the break, but it's the amount of information that's encoded is exactly the same. This is the most compact way to encode the information. Let's talk in the break. Okay, it's not true, but let's talk in the break. Yeah. If there was order, if there were ordinal variables, there is a shorter way of doing it. Without order, this is the most compact way of doing it. Yeah. So the best fit line does not care about the range of values. The best fit line does not care about the range of values. You could have three variables. One variable could extend from all the way from 120 to 1,375,000. The other variable can be from 0.1 to 0.3. The slope for each one is going to be computed separately. The magnitude of those do not matter. That's what you're asking, right? Yeah, it does not matter. Any other question? No, this is good. This is generating discussion. That's always very good. And I know what you're thinking. It looks like it can be compacted more, but not in ordinal cases. It can be compacted. But let's talk about that. So in the case of consider the issue of sex discrimination in salary earnings of workers in some industry. So for a given data set, you want to find out if there is a discrimination of how much one gender is earning more than the other. The data set is actually given. What the data set contains is earnings, which is what you're trying to predict if there is an influence of, let's say, Y value, age, and the sex, as in male or female. Okay. The way you do that is the categorical variable, male or female categorical variable. You're going to convert. It's got two options. You're going to convert that into one dummy variable of 1 or 0, right? As long as you have n categories, it can be converted to n minus 1, right? So we are converting this into 1 or 0 value. Once it's a 1 or 0 value, it's a numerical number. You can do linear regression. Put it through Excel, and this is the output that you're getting. Is the model significant? Model is significant. Are the independent variables significant? Age is not significant, right? The sex is significant. Age is not significant, which means the experience doesn't matter. What matters more is whether you're a male or a female. Can you tell who earns more? According to this data. See, this value is all used to check whether the value of the slope is significant or not, right? That we have looked at the p-value and decided is significant. Okay. Now I'm asking you to interpret this. When it is, sorry, is the intercept significant? Intercept is significant. Okay. Easiest way to check who's earning more is there are only two values to check, right? 0 or 1 are the two values that need to be checked. 0 is easy to compute. What is the salary when it's 0? 1.73 is a salary when it's 0. When it is 1, 1.73 plus some coefficient. So who's earning more? Male is earning more. Clear that there is a sex discrimination that is there in your data set is showing sexual discrimination, right? So here is something where you're putting a categorical variable and then using that to make your forecast. Okay. The way you do that is convert that categorical variable with n categories to n minus 1 dummy variable and do a simple linear regression. Any questions? Yeah. Excellent question. What happens? What do you think will happen? Right. So when you change it in your data set, the ones will be replaced by 0 and zeros will be replaced by 1. So now it's a different data set. So you need to do a refit it separate, right? You need to refit it. When you refit it, you will get different values of slope. What do you think is going to be the sign of that slope? It's going to be negative. Yeah? Yeah. Yeah. Hmm. Okay. So, um, good question. Let's make sure we completely understand this. So uh, let's see that. Let's say that we are considering the example of price of the house. Okay, price of the house based on square footage and region of the house, region that where you are talking about. Okay, just to keep it simple, only two independent variables. So you have y is the price of the house, and here is the square footage, and then its region. Okay, so I have I don't know, some number. This thing I'm putting some number there, and here it is north, 18.5, east 13.4, west, so on. Okay, what I'm going to do is, I said that I'm going to convert this into three separate variables. So instead of this, I'm going to call it as uh, uh, north region, um, south region, west region. Okay. If without before the region was done, like without this data, if you had actually done regression of this, you would have gotten an equation that looks like this. Price is equal to some alpha times square foot plus some constant. This is what you would have gotten without putting into account the taking into account the region. Okay. Now I'm giving you new information, so you need to redo the regression and seeing if you are getting a better fit or not. This has got four categories. I'm splitting it into three categories. Right? When it is north, this region gets 1. These are all zeros. When it is east, all of them are zeros. When it is west, this is 0 and this is 1. Correct? Now, the regression equation is going to look like this. Price is equal to a different value. The square footage slope could change because now you're looking at a new data set, right? So the values of all of this is going to be different. So it's going to be A times square foot plus B times north region plus C times south region plus D times west region plus some constant. Okay, this is what it's going to look like. When we are talking about north, okay, now you are trying to, so you have a best fit line and you need to make a forecast of a new house whose square footage is given and it's in the northern region. You want to make a forecast on what is the price of that house, right? So when it is in the north region, what's going to happen? The square footage value is given. When it's the north region, this north value becomes 1, right? This becomes 0, this becomes 0, right? So for the price of this new house that is in house I that's in north has going to have a value A times square foot plus B plus this constant, right? A different house that is in east is given. how is the equation going to look like? A times square foot, all of these guys are going to be 0 plus this constant C, right? So ultimately what's happening is when you are doing this fit, the region of the house is going to give you different effective value of intercept. Do you understand that? Thus, these terms are effectively becoming a new intercept. In this case, it's B plus constant. In some other case, it will be C plus constant. In the third case, it's going to be D plus constant. So what about the fourth case? Fourth case was the original constant. Okay. So that's the way it accounts for these categorical variables. It's telling you for each categorical variable by how much is the intercept change. Is the idea clear? Correct. You should not put this. You should do a best fit with square foot on this and then use that. Correct. Absolutely. 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 I mean, we don't have information on number of bedrooms here. You try to do the best fit. You try to work with the data that you have. Yeah. Very good question. What will happen often is your data set might not have equal number of north, east, west data points. The number of data points are going to be uneven. Linear regression mechanism, there's nothing that you're going to do different. You're still going to do exactly the same. What is, however, going to happen is the standard error corresponding to those coefficients are going to be different. But the procedure itself that you're going to follow in computing it, none of them is going to be changed. Sorry, one second. Yeah. It might be that sample is not picked correctly, but this is the data that you have. I mean, maybe the sample was collected from sales last year. In the west, not many sales are happening versus east, or the other way. East, not many sales are happening versus west. What do you do? That's the data you have. You're trying to work with the data that you have, and that will be reflected in the standard errors of those coefficients. Yeah. 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 Plus some intercept. No, the coefficients are 0, but there will still be a one regular intercept. That is the intercept corresponding to the case where all are zeros. Yeah. Okay. Let's. The next section is an important section where we are doing feature selection and model building. So let's take a quick break and then come back. The numbers will change, but what you will get will be the slope is going to be minus. It's going to be minus 0.45, and the intercept would have been higher by that amount. Okay, so let's talk about feature selection. But before I do that, so your colleague suggested alternate method of encoding this using a base 2 thing. It seems more compact way of doing it. I haven't been able to find why that shouldn't work. As of now, it looks like that might also work. But the way it's traditionally done is the way I talked about. I need to verify it. Let me look at it and take some examples and convince myself that both will give me the right answer. Then we can have another thing. But it was an excellent suggestion of that you can code it using log2 based variables. instead of using n minus 1 variables. It will be more compact coding. Sorry? Right. Right. Yeah. So what will happen is you round it up. Whatever your log to your number you're getting, you round it up. That's what he would say. That will still be less number of variables than this. But let's not get into that discussion yet because I don't. I haven't actually worked it out. I haven't tried it, and I'm not sure if there is anything wrong with it. Nothing seems wrong right now. I need to check it. I want. So the outlier discussion is separate from all of this. This is how do you set up the regression equation. Once you do the regression equation, you need to do the residual plot that will show you the outliers. And if it is an outlier, you need to still handle it the way we talked about yesterday. Right. Correct. Correct. Right. That by itself doesn't this thing. But you know what? I don't want to this thing. We'll talk about that separately. This thing. That outliers is not based on that. Outlier is based on how far away it's from the fit line, right? So we'll talk about that separately. Let's move on to feature building. Yeah. So excuse me. So the question that's asked is this: in the example that I gave here, right, where you have a data of price of the house, square footage of the house, and the region of the house, right? For this, we got this particular equation, right? What this equation is doing is it's effectively assigning the same slope for all of the regions and different intercept for each one of the regions, right? The underlying base level is different, but the same slope is being given to all of them. Her question was, if you restricted the data set, took only north, okay, did a linear line fit on that, then took only south, did another linear line fit, will I get the same answer? You won't get the same answer. You are trying to do a best fit for each region separately. What we are doing here is trying to do a single fit for all the regions together, but also taking into account the values of the region. So this is in nature a different data. That fit would require a smaller subset, right? Each one will be a smaller subset, and the fit will be seeing smaller subset of data. So the fit will be different. Price estimation will be different. Yeah. Yeah. The error, yeah, the standard error in each case when you do a fit, it will give you a standard error. So if you do 4 fits, you will get 4 separate estimates of standard error. In this case, you will get one standard error. Yeah. So let's move on. This is a very important topic: model building and feature selection. Okay. What I'm showing you here is the empty cars database, the data set which has miles per gallon with various other features of the car, like the weight, horsepower, time to travel, quarter mile, and all of that. Now, this data, ultimately, we are trying to figure out what is the best way to predict the miles per gallon based on available set of features, right? When we started the analysis, we initially did miles per gallon with weight. That's the very first fit we did, right? Very first class of statistics, we talked about trying to, as the weight increases, miles per gallon drop, right? We have this notion that as we keep adding more information, we'll be able to do a better fit, right? But the question is that really true? does adding more variable results in a better figure? Okay. If so, how many variables is actually the right one? I mean, does it mean that you can add the color of pants of the driver? Would that improve your fit? Well, it's unlikely, but is there a systematic way of figuring out what is the number of variables? How many variables do you need to make this? That's what this discussion is all about. So here, what I'm trying to do here is I'm trying to fit miles per gallon with two variables, weight and horsepower. Okay. Is the model significant? 10 to the power minus 12. Definitely significant. How about the variables? Are the variables significant? Even if you cannot read the numbers, you can see stars everywhere, right? So clearly the model, the variables, both these variables, weight and horsepower are useful in describing the miles per gallon. Let's say suddenly I increase one variable. So weight, horsepower, and time taken to travel quarter mile, right? So now three variables are there. And I do the fit. What can you tell about the variable's significance? Weight seems to be significant, but the horsepower and time taken for quarter mile, both of them do not seem significant. Does that make sense? We just found that horsepower was significant. By adding more information, this one should still remain significant. I added more information, and suddenly it turns out that it doesn't seem significant. Let's look at the adjusted R square, right? It's 0.8148 here. Over here it's 0.8171, about the same. So the fit seems still good. But adding that extra piece of information suddenly seems to make the thing not significant. That doesn't make intuitive sense at all. In fact, let's take one step further. Let's add all variables. When I added all the variables, none of them are significant, including the intercept. Is the model significant though? The model is 10 to the power minus 7. The model is significant. What's happening? Adding more of them, suddenly now, things that we learned till now, so how to understand this significance, the way we understood it does not gel with what we are seeing here. Okay. So one thing is certainly clear. Adding more variables does not seem to be always the right thing to do. Okay. We'll talk about exactly why this is happening, but does not seem to be the right thing to do. So we need to have some limit on number of variables that are needed to completely describe the particular model. And as I already talked about earlier, right, there's this idea of Occam's razor, where you have this notion that simpler the model, the better it is, right? So can I find out what would be the absolute minimum set of variables that are needed to describe this particular problem? That's my problem statement. Okay, trying to find the absolute minimum set of variables to describe it. So the way we are going to talk about it is through an example. I have a data set here, US, which contains the US energy consumption, the US nuclear energy generation, US coal production, dry gas production, and fuel rate. All of this data is given to us, and we are asked to predict world crude oil production using these numbers. Okay, so we have world crude oil production is what we need to forecast. That's our Y value, and we are given 1, 2,